The second part of chapter 9 is about state space models in discrete time, so where time is no longer a continuous variable, but instead time consists of discrete time steps. Most students, especially those coming from an engineering background, are usually less familiar with discrete time systems than with continuous time systems. This may be different, however, for some students who come from a computer science background. In reality, discrete time systems arise either naturally, if we have a dynamic system that works on discrete time periods, or they appear as a result of sampling a continuous time system, which is something that happens very frequently given the digitalization in measurements and control. Anyways, in this course, we cover both continuous time and discrete time systems with an equal weight. Analogously to the continuous time state space model, in the discrete time state space model, the time-varying system matrix A is now a function of the discrete time step k, and the same is true for the time-varying input matrix B of k, the time-varying output matrix C of k, and the time-varying throughput matrix D of k. Hence, a discrete time linear state space model is defined by equation 18, consisting of a state equation and an output equation, where the state equation updates the state at the next time step, so x k plus 1, which is equal to ak times xk plus bk times uk, where xk is the state at the previous time step and uk is the control input, and the output at time k, y of k, is given by c of k times the state at time k plus d of k times the control input at time k. And of course, the system also starts from some initial condition where the state at the initial time step k0 is given by some vector x0. Again, if there is no external control input to influence the system, so the input matrix B of k and the throughput matrix D of k are both 0, then we speak of an autonomous system. So clearly, in this case, the discrete time linear state space model is called a discrete time linear autonomous system, and it looks as shown in equation 19. Again, in analogy to continuous time systems, if the system matrix, the input matrix, the output matrix, and the throughput matrix are all time invariant, then we call the discrete time linear state space model, or the discrete time linear autonomous system, a linear time invariant system. As some of you may know already, analogously to the frequency domain and the Laplace transformation for continuous time systems, there also exists a frequency domain and a so-called Z-Transformation for discrete time systems. And this Z-Transformation is defined as shown in definition 9.17, where it's assumed that a function f of k of discrete time k is given. The function f is valued by a general m by n complex matrix, and the z-transform of f is then a function capital F, which maps from a complex frequency domain variable, again into the space of complex m by n matrices, and it's defined by this infinite sequence shown in equation 21, where the complex frequency variable is denoted as z, and f of z is equal to the sum from k equals 0 to infinity of the function f of k multiplied with z to the minus k. Or by spelling out the sum, f of z is equal to f of 0 plus f of 1 times z to the minus 1 plus f of 2 times z to the minus 2 plus f of 3 times z to the minus 3, and so on. Note that in the definition of the z-transform of the function f, the expressions f of k represent m by n matrices, whereas z to the minus k are scalars. The summation is interpreted element-wise, and therefore f of z is also an m by n matrix. In terms of notation, just as for the Laplace transformation, we will use capital letters, like this capital F, to denote the z-transform of a time domain function f of k, and we will use the calligraphic letter z to denote the z-transformation applied to a time domain function f of k, and a calligraphic z with a -1 in the superscript to denote the inverse z-transformation of a frequency domain function f of z. Similar to the Laplace transformation, the z-transformation also has a certain convergence region in the complex plane. In fact, as stated in Theorem 918, for a given time domain function f, the corresponding z-transform exists outside of a circle with a certain radius r if all elements of the time domain function fij of k are asymptotically bounded by a geometric sequence, which means that there must exist a positive constant c and a natural number n such that each matrix element fij of k must be bounded in absolute value by c times r to the k, which must hold for all time indices k beyond the time index n. This condition is obviously an analogy to the condition that continuous time functions may grow at most exponentially in order for their Laplace transform to exist. And just as the exponential condition for the Laplace transformation, this condition here is fairly general, and it will be satisfied by almost every time domain function f. For the purpose of using the z-transformation, it's sufficient that the z-transform converges outside of a circle with some radius r, so we don't really care about the convergence region, and we may just say that the z-transform of a time domain function exists if all of the elements fij of k are asymptotically bounded by a geometric sequence, which is why we may put the actual convergence region in brackets. Just as for the Laplace transformation, the proof of convergence is actually fairly simple. First, we fix a row index I and a column index j. Then we consider all time indices k which are greater than n, such that fij of k in absolute value is bounded by c times r to the k. Then we multiply each side with the absolute value of z to the minus k, which yields this inequality. And then we observe that the right-hand side can also be written as c times the absolute value of r divided by z to the power k. This element-wise inequality can now be substituted into the definition of the z-transformation, which shows that the z-transform of f is bounded by a geometric series that is known to converge whenever the absolute value of r divided by z is less than 1, or in other words, if the absolute value of z is greater than r. Of course, there's also an inverse z-transformation defined in an elementary way, as shown in fact 9.19. However, this elementary definition is rarely used because in practice we can refer to z-transformation tables in order to perform the inverse z-transformation. However, for the sake of completeness, if f is a well-defined function outside of a circle with radius r in the complex plane, then the corresponding time domain function f is given by the formula in equation 22, stating that f of k is equal to 1 over 2 pi j times the contour integral of f of z times z to the k minus 1 dz, where c represents any contour line in the complex plane that encircles the circle of non-convergence once in the counterclockwise direction. As before, the integral over a matrix-valued function can be interpreted as an element-wise integral. Now let's look at some examples for the Z-transformation. And the first example is for the unit impulse function delta, which is defined as delta of 0 is equal to 1 and delta of k is equal to 0 for all k greater than 0. By simply applying the definition of the Z-transformation in equation 21, we get that the Z-transform of the unit impulse function delta is given by 1 plus 0 times z to the minus 1 plus 0 times z to the minus 2 and so on. So this is simply 1. Next, we look at the Z-transform of the discrete unit step function, which is denoted by the Greek letter upsilon, and which is defined by upsilon of k is equal to 1 for all non-negative k. And again, to find the Z-transform of the unit step function, we apply the very definition of the Z-transformation in equation 21. And if we apply this formula here, we get the infinite series of 1 plus z to the minus 1 plus z to the minus 2 and so on, where we take out the factor of z from each of these infinitely many terms. And what we are left with then is, in brackets, z to the minus 1 plus z to the minus 2 plus z to the minus 3 and so on. Therefore, it follows that z of upsilon minus 1, which is equal to this infinite series, is equal to z to the minus 1 times z of upsilon, which is also equal to this infinite series. And solving this equation for z of upsilon yields 1 over 1 minus z to the minus 1. Let's also look at two slightly more difficult examples for the Z-transformation. In the first one, f of k is given as alpha to the power k, where alpha is any complex value. In this case, the Z-transform of f of k is given by 1 over 1 minus alpha times z to the minus 1. And the derivation of this result will be an exercise on the next sheet, number 10. In the next example, f of k is given as the sine of omega times k, where omega is given as a real value. For the derivation of the Z-transform f of z, we first apply Euler's formula, which states that e to the j omega k is equal to cosine of omega k plus j times sine of omega k. And correspondingly, e to the minus j omega k is given by cosine of omega k minus j times sine of omega k. Hence, subtracting the two equations yields that e to the j omega k minus e to the minus j omega k is equal to 2j sine of omega k, and if we add the two equations, we obtain that e to the j omega k plus e to the minus j omega k is equal to 2 cosine omega k. From the definition of the Z-transformation in equation 21, we get that f of z is given as the sum over k from 0 to infinity of sine omega k times z to the minus k, where we can now substitute this equation, which we call star star, in order to get the sum over k from 0 to infinity of 1 over 2j times in brackets e to the j omega k minus e to the minus j omega k times z to the minus k. This sum can be split into two sums, one involving e to the j omega k, which can also be written as e to the j omega in brackets to the power k, and the other one involving e to the minus j omega k, which in a similar fashion can be written as e to the minus j omega in brackets to the power k. Thus, we realize that in both cases these infinite sums correspond to the definition of the Z-transform of a function like f of k equal to alpha to the k, where in the first case alpha is equal to e to the j omega, and in the second case alpha is equal to e to the minus j omega. Hence, with the formula in star, we obtain that f of z is equal to 1 over 2j times 1 over 1 minus e to the j omega z to the minus 1 minus 1 over 2j times 1 over 1 minus e to the minus j omega z to the minus 1. Next, we take out the common factor 1 over 2j, and we expand both fractions by a factor of z to obtain this expression, and then we form the least common denominator of these two fractions, and we obtain this large fraction as a replacement for the difference between these two fractions. This large fraction can be further simplified by multiplying out the corresponding factors in the numerator and denominator, and noting that in the numerator z square cancels with minus z square here, and we're left with z times in brackets e to the j omega minus e to the minus j omega, and in the denominator, if we multiply these two brackets out, we get z square minus in brackets e to the j omega plus e to the minus j omega times c plus 1. By substituting k equal to 1 into equation star star, we notice that the expression in this bracket here is equal to 2j times sine of omega, and similarly by substituting k equal to 1 into equation star star star, which is this equation here, we notice that the expression in this bracket is given by 2 times cosine omega. By just cancelling the factor of 2j, we obtain that the Z-transform of sine omega k is given by z times sine omega divided by z squared minus 2 cosine omega times z plus 1. In a similar fashion, many more Z-transforms of different discrete time functions f of k can be obtained, and the most important ones are summarized in the table shown on this slide. And of course, they can also be used to obtain the Z-transformation of other time domain functions, or conversely, to perform the inverse Z-transformation of given transformed functions. Moreover, for the Z-transformation, we have a bunch of useful properties as stated in Theorem 9.20. Namely, A, the Z-transformation is linear, so Z of a linear combination of two functions f and g by two scalar factors alpha and beta is equal to alpha times f of z plus beta times g of z. B, for the right shift operator, which we have already introduced earlier in this lecture, we have that z of sigma to the minus n of f of k is equal to z to the minus n times f of z. C, for the left shift operator, we have that z of sigma n of f of k is equal to z to the n times, in brackets, f of z minus the sum over k from 0 to n minus 1 of f of k times z to the minus k. D, the z transformation of the first difference backwards, so z of f of k minus f of k minus 1 is equal to, in brackets, 1 minus z to the minus 1 of f of z. And E, the z transformation of the first difference forwards, so z of f of k plus 1 minus f of k is equal to, in brackets, z minus 1 times f of z minus z times f of 0. And finally F, if we have a convolution in the time domain, so f convolved with g of k, then the z transformation results in a simple multiplication of the z transforms of the functions f and g, so f of z times g of z. If you have not seen the convolution of two discrete time functions before, the definition is stated at the bottom of the slide. So if we have any two sequences f and g, the convolution f convolved with g is defined as follows. The kth element of the convolution is given by the sum over I from 0 to k of f of k minus I times g of I. Analogous to the Laplace transformation, for the z transformation, we also have an initial and final value theorem. The initial value theorem states that if lowercase f is a discrete time function and uppercase f is its z transform, then f of 0 is given by the limit of z going to infinity of f of z. And the final value theorem states that if lowercase f is a discrete time function and uppercase f is its z transform, then the limit of f of k as k goes to infinity, if it exists, is given by the limit of z going to 1 of, in brackets, z minus 1 times f of z. Let's look at a small example application for the z transformation, which also helps to review some basic mathematical techniques that are needed in the context of the Laplace transformation. Just like any mathematical technique, there is no problem that can be solved with the z transformation that cannot be solved without it. However, in some situations, the z transformation can make the solution significantly simpler. For this example, suppose that y of k for k greater than or equal to 0 is a sequence that's given implicitly as the solution to the following difference equation, namely y of k plus 1 is a times y of k plus b times upsilon of k for some initial condition y of 0 is equal to y0. In this equation, a and b are two constants, where a is not equal to 1 and b is not equal to 0, and this upsilon of k here is the unit step function. For instance, you could interpret this equation as the dynamics of a savings account, where y of k represents the account balance in the discrete time period k, a being equal to 1 plus d represents the growth of the account balance over one period, where d is the interest rate that is paid on the account balance in each time period, and b is a constant amount that's being paid into the account in each time period k. Of course, y of 0 represents the initial account balance. Our objective here is to find an explicit expression for y of k. If we want to apply the z transformation, the first step is of course to apply the z transformation to this entire dynamic equation. This yields that c of y of k plus 1 is equal to c of a times y of k plus b times epsilon of k, where by theorem 9.20c, the left-hand side is equal to z times y of z minus c times y of 0. And by linearity of the Z-transformation, the right-hand side is equal to a times y of z plus b times the Z-transform of epsilon of k, which by the table for the Z-transformation is equal to 1 over 1 minus z to the minus 1. Step 2 is always to solve for the Z-transform of the desired solution, so in this case for y of z. This is accomplished by simple algebraic manipulations. So we first bring all terms involving y of z to one side, which is this z times y of z minus a times y of z. And then we bring all other terms to the right-hand side, which is plus z times y of 0 plus b times 1 over 1 minus z to the minus 1. Then we take out the common factor y of z on the left-hand side, and we expand this fraction by a factor of z in order to obtain this equation, where y of z now follows by a simple division by z minus a, and it's equal to z divided by z minus a times y0 plus b times z divided by z minus a in brackets and z minus 1 in brackets. Step 3 then consists of applying the inverse Z-transformation in order to solve for y of k. So y of k is obviously equal to the inverse Z-transformation of y of z, which by the result up here and the linearity of the Z-transformation is equal to the inverse Z-transformation of the first term plus the inverse Z-transformation of the second term. The inverse Z-transformation of the first term is obtained by a simple lookup in the Z-transformation table, hence it's equal to a to the power k times y of 0. For the inverse Z-transformation of the second term, we need to perform a partial fraction expansion. It's assumed that you are familiar with how to perform a partial fraction expansion, and hence we go over this fairly quickly. First, we write this fraction here as the sum of two fractions, the first of which consisting of a constant c divided by the first factor, z minus a, and the second one consisting of another constant d divided by the second factor, z minus 1. Now we need to determine the two constants c and d, and to this end we form the least common denominator of these two fractions, which is of course equal to the denominator of this fraction here. Then the numerator can be written as a polynomial of z, where we first combine all terms multiplying z, and there we get c plus d times z, and then we combine all constant terms, where we get minus, in brackets, c plus dA. A comparison of the polynomial coefficients of the numerator on the right-hand side with the numerator on the left-hand side leads to two equations for the two constants c and d. The first equation reads as c plus d must be equal to 0, and the second equation reads as minus c plus dA in brackets must be equal to 1. Solving the first equation for c, we get that c must be equal to minus d, and if we substitute this into the second equation, we get that d times 1 minus a must be equal to 1, or d is equal to 1 over 1 minus a. And hence, with equation 1, c must be equal to minus 1 over 1 minus a. Substituting these results for the two constants c and d up here and replacing this fraction with the two fractions in the expression up here, the inverse C transformation that we want to compute can be written as the inverse C transformation of the sum of two terms. Now we can again use the linearity property of the Z transformation in order to pull this inverse C transformation apart into these two inverse C transformations. And these two inverse C transformations can now be solved based on the Z transformation lookup table, where we find that the inverse C transformation of this first expression is given by a to the power k, and the inverse C transformation of the second expression is given by the discrete unit step function y of k. So the complete solution for y of k is obtained by combining the single term that results from the inverse C transformation of this expression, which was calculated as a to the k times y naught, and the two terms resulting from the inverse C transformation of the second term, namely these two terms, which can be combined to b over 1 minus a times in brackets y of k minus a to the power k. Equipped with this knowledge, we now proceed to the solution of discrete time state space models, beginning in Theorem 9.23 with the solution to a discrete time linear time invariant autonomous system given in equation 23 in the time domain, which is given by y of k is equal to c times a to the power k minus k naught times x naught. The proof of this result is fairly obvious. Note that we have x of k naught is equal to x naught by the given initial condition. And then to get to x of k naught plus 1, we have to multiply x of k naught by the matrix A. So we get here A times x naught. To get to x of k naught plus 2, we have to multiply x of k naught plus 1, again with the matrix A. And doing this for A times x naught, we get to A squared times x naught, and so on. So we see that x of k must be equal to a to the power k minus k naught times x naught. And now to get to y of k, we just have to multiply x of k with c. So this proves our claim. Since the solution to the discrete time linear time invariant autonomous system for any initial condition x naught at any time k greater than or equal to k naught is given by the formula that we have just proved, we can define a to the power k minus k naught as the fundamental matrix of the discrete time system, denoted capital Phi with an index d, and with the arguments k and k naught. As we shall see shortly, the fundamental matrix Phi d is not just relevant for the discrete time autonomous system, but also for the general discrete time state space model. By the very definition of the fundamental matrix, it's easy to verify the fact stated in proposition 9.24, namely that the fundamental matrix for any k greater than k naught satisfies that phi d of k and k naught is equal to phi d of k minus k naught and 0. Analogously to the continuous time case, we can now extend the results of the discrete time LTI autonomous system to the discrete time LTI state space model, whose solution in the time domain is given by this formula, which consists of two parts, both of them containing the discrete time fundamental matrix phi d, and the first one depending on the initial condition of the system x naught, and the second one depending on the control inputs u of k. Note that similar to the continuous time case, in the second term we have a discrete time convolution between the fundamental matrix and the input sequence u of k. Just as for the discrete time autonomous system, this solution formula can be proved by a simple induction. So we start with the state at the time instance k0, which is equal to x0 according to the initial condition. And then we calculate the next state x at time k0 plus 1 by using the system equation. So this is equal to a times x of k0 plus b times u of k0, which using this equation is just equal to this expression here. Then we can do the same thing for the state x at the time step k0 plus 2, which is given by a times x of k0 plus 1 plus b times u of k0 plus 1, where we can now substitute this state by the formula up here to obtain this formula, and we can go on in the same fashion. Generalizing this, we see that the state sequence x of k is given by this formula here, so that the output equation of the state space model leads to the desired result. Finally, Theorem 9.26 states the solution to the discrete time linear time invariant state space model in the Z domain, which is given as the Z transform of the output y of z is equal to the sum of two terms, the first of which involving the initial condition x0, which is multiplied by this expression, and the second of which involving the Z transform of the control inputs u of z, which is multiplied by this expression, which is also defined as the transfer function of system 20, often denoted as g of z. Again, the proof of this result is fairly simple. All we need to do is to apply the Z transformation to the state equation of the state space model, which using the left shift operator in Theorem 9.20c yields that z times x of z minus z times x naught is equal to a times x of z plus b times u of z, where we can bring this term to the right-hand side of the equation and this term to the left-hand side of the equation in order to obtain this equation, where we now just need to multiply with zi minus a inverse to obtain x of z, and then we use the Z transformation of the output equation, so y of z is equal to c times x of z plus d times u of z to obtain the desired result. By a simple comparison of the results in Theorem 9.25 and Theorem 9.26, we can immediately deduce corollary 9.27, namely that the Z transform of the matrix A to the power k must be equal to, in brackets, zi minus a inverse times z. Or, in other words, the Z transform of the discrete time fundamental matrix is equal to the resolvent of A times Z. The final slide of this chapter summarizes the main results that we have obtained for the continuous time state space model and the discrete time state space model. First, the fundamental matrix in the continuous time case is given by the matrix exponential e to the power a times t minus t naught, and the fundamental matrix in the discrete time case is given by a to the power k minus k naught. Then for the continuous time case, we have the Laplace transformation, and in particular, the Laplace transformation of the continuous time fundamental matrix is given by the resolvent of A. For the discrete time model, we have the Z-transformation, and the Z-transformation of the discrete time fundamental matrix is given by the resolvent of A times Z. In both the continuous time case and the discrete time case, the solution for the state trajectory splits into two parts. The first part is the free response, which depends only on the initial condition, and which in the continuous time case in the time domain is given by this formula, and in the Laplace domain is given by this formula. Similarly, for the discrete time model, the free response is again the part that only depends on the initial condition x0, and in the time domain it's given by this formula, and in the z domain it's given by this formula. The second term of the state trajectory is the so-called forced response, which does not depend on the initial condition x0, but it only depends on the control input signal u. In the continuous time case, it's given by the continuous time convolution between the fundamental matrix and the input signal, and in the discrete time case, it's given by the discrete time convolution between the fundamental matrix and the input sequence u of k. And these are the corresponding frequency domain transformations of the forced response of the state trajectory. Last but not least, in both the continuous time case and the discrete time case, we can define the transfer function of the system, which for the continuous time case is given by this formula for g of s, and in the discrete time case it's given by this formula for g of z.